the 11th.
Yeah, a week from Thursday. So that is coming up. So we're going to finish as much as we can, finish chapter 6 Thursday. Anything we don't finish, we'll leave for next Tuesday. And we're going to do a lot of review next Tuesday. And then you have the exam next Thursday. So I have a bonus point opportunity I'm about to tell you about for the exam. I'm going to post this to Blackboard. And if you will download it or print it and do this worksheet, and then what I'm hoping is that you can upload this to a discussion board on Blackboard as proof to show me that you did it. So you need to take a picture of it or scan it or whatever, upload it. And if you do it, and if you do it correctly, then you will get up to 5 bonus points for exam 2. So I'm going to share my screen and show you what this is. It is a worksheet that will also help you study for the exam right here. So this is a worksheet classifying chemical reactions. Basically, you're going to classify each reaction. Today, we're going to learn acid-base redox and precipitation reactions, okay? So, and then also you already know the synthesis, decomposition, single, double, or combustion, okay? So you have these reactions here. There's 15. This is great practice for the exam. And then the equations are not balanced. So you go through and balance them, and then you look at how to classify them. And we're going to learn the rest of the ways to classify today. And I'll be straightforward with you. There are like certain reactions you can classify more than one way. Okay, so for example, 4 right here. 4, you might look at it and be like, oh, 2 things coming together. Okay, so I know I can classify that one way. Well, there's another way you can classify it that we're going to learn about today. So there might be 2 ways to classify it, and you would need to write both ways on certain reactions that you recognize. Okay, so this worksheet I will post to Blackboard. I'll send an email out when I post it, and or I might send it in the email. I'm not sure yet, but I will let you know when it's distributed and available, and you can work on this and do it. And you need to have it uploaded before next Tuesday, because we're going to go over the answers for it next Tuesday. Okay. And that will also help prepare you for exam too as well. Any questions on this?
So you want us to balance it as well as classify it?
Balance.
Okay.
Yep. So write your little coefficients in there. You probably just need to write small because you have to squeeze them in. But I would prefer you not write this on your, I mean, if you need to write it on your own sheet of paper, I understand, but if you can print it and do it on this, that would really help me a lot. So please try to print it and do it on this. Okay, so there's that. And I think that's all I have for now. We are going to do another review type thing next Tuesday. I'm going to save some time for that. And it is going to involve us playing my goal, the way we're going to do it. Last time we kind of did that pop quiz thing where I had you put away all your notes and get out a sheet of paper, and I timed you and we moved through some slides and worked some problems. And I talked to some people yesterday. I think what I'm going to try is a game of Kahoot. Anybody played Kahoot before? Okay, I see some head nods. Kahoot is really fun. Please turn your video on if you can join us this morning. Got a lot of you with video off this morning, so please join us if you can. Kahoot is free, okay, and I'll give you the game pin, and you'll go to, I'll tell you what website to go to, and you'll just type in the game pin, and it'll be multiple choice style questions, and it'll be timed, so it's going to still simulate that exam feel with things being timed. And it will give you a really good idea of kind of where you're at, the lay of the land with the 4, 5, and 6 chapter material. And that way you can help focus what you need to study on leading up to the last day or 2 before the exam, okay? So that's just a heads up for that. But I think that's all my announcements. So we are halfway through chapter 5, and I'm going to get over to the iPad, and we are going to pick up with the material. But I did want to go over one poll question from chapter 4 stuff, because I never really got to do as good of a review on some of the polar molecule stuff as I had wanted to. So I'm actually going to jump over to my molecular compounds lecture, and I'm going to remind you of one thing. We talked about the idea of polar molecules. You remember this? Polar molecules. And we said there's 3 things that you need to remember when determining if a molecule is polar. but this was towards the end of lecture, and we kind of had to move through it fast, and so that's why I wanted to come back and hit it really quick. So chapter 4, one of the big things was we talked about polar bonds and then polar molecules. So when you're looking at a molecule and trying to decide if it's polar, you need to assess 3 things. Does it have any polar bonds? Does it have any lone pairs? And then the shape. Okay, is there symmetry? If there is symmetry, remember we looked at 2 examples down here. We said there's no net polarity if a molecule is symmetrical, and you can draw in 2 dipoles that cancel out. Okay, so then there were some more examples. I hope you looked at those on the next slide. If you haven't, please do look at them. I worked a few with some students, or a student that had a question, so that's why this slide is drawn on. But I had a poll question, so I want you to look at these molecules right here, and I'm going to launch the poll. I want to see how much of this we remember. So here it is. Which of the following molecules is not polar? And if you need to draw out the Lewis structures, grab a sheet of paper and do so. Okay, which one is not polar? So all of these are polar except for one. And please do not just guess. Please actually assess the 3 things we mentioned. You need to look at the Lewis structure. You need to ask yourself, are there any polar bonds here? Remember, how do we determine if a bond is polar or not? It all has to do with electronegativity differences. If you need the chart for electronegativity difference, it's somewhere. I think it's a few slides up. I'm going to give about 30 more seconds, and then we're going to talk about this one. And you may feel rushed on this, but at least just wanted to give this a small review. Okay, I'm going to shut it down in just a second because we're only 70% voted. Give it a few more seconds. Almost there. All right, we're almost 90%. If you haven't got your vote in yet, go ahead and put it in. I'm about to shut it down. All right. Let's look at this. So, share results. Okay. So the most commonly guessed answer was CH3Cl. And the next most commonly guessed answer was, I should say selected answer, I'm not going to assume everybody guessed, would be CO2. And sorry, I cannot type those numbers in as subscripts on a Zoom poll. All right, so let's look at the answer here. So the correct answer should have been CO2. This one is not polar. Okay, but let's look at the other ones to see why. I'm going to draw these out really quick. You got NH3, looks like this. So at this point in the game, I expect you to be relatively quick with your Lewis structures and feel good and confident with those. Okay, the next one is water. Okay, the next one is CH3. You could have drawn this a couple different ways with your Cl or your H's in different places, but it all ends up being about the same thing. You got lone pairs all over that chlorine, and then you got CO2. Okay, we actually looked at CO2 from our lecture. Okay, that one's right up here in the slides. I'm going to erase all this. This is CO2, and we looked at this and we assessed the fact that there are polar bonds, but then remember we said there's 0 net polarity because there's symmetry here. Okay, so I'll come back to that. We also looked at a molecule of water from lecture. Okay, so if you remember this, we looked at water and we said, oh, water does have a permanent dipole that we can draw in towards the partial negative region of the molecule. Okay, so first off, do these molecules have polar bonds? All right. If you calculate the electronegativity difference between nitrogen and hydrogen, yes. All of these bonds right here, the nitrogen-hydrogen bonds, they're all identical bonds. It's a single nitrogen-hydrogen bond. These are all polar. Okay, so these are polar bonds. Check. We got a lone pair on nitrogen. Okay, so we got a lone pair. That's another check. And is this molecule symmetrical? No, it's not. Okay. We can draw the dipole in. This would be, the hydrogens would be the partial positive region. And then the lone pair would be the partial negative region. And we can draw a dipole in pointing towards the partial negative region, and it does not cancel out with anything. So that one's polar. Same idea with water, okay? The oxygen hydrogen bonds right here, these are polar. So we got polar bonds. We got two lone pairs on oxygen, okay? So lone pairs, check. And is it symmetrical? No, because again, we can draw the partial positives on the hydrogens. These are the electron poor region of the molecule. The lone pairs are the electron dense or rich region of the molecule. So we can draw the dipole in pointing towards this way. Now, some people might be like, well, yeah, you can draw a plane of symmetry right down through, I got something in the chat, right down through the middle, but the dipole doesn't cancel with anything, okay? The dipole doesn't cancel. So that's what you're looking at. So this is polar as well. Same idea with CH3Cl. I'm just going to go ahead and draw. Your hydrogens are now are partial positive, and the chlorine is partial negative. Now the carbon hydrogen bonds, these bonds right here, these are not polar bonds, okay? None of these are polar. Remember, carbon hydrogen bonds are never polar, but this bond right here is a polar bond. The carbon chlorine bond is polar, okay? So remember that. So we got a dipole that we can draw right there. But CO2, these bonds, these are polar bonds. And then we got lone pairs all over the oxygens. So the oxygens are going to be your partial negative region of the molecule. The carbon is the partial positive. You can actually draw two dipoles in, okay, pointing towards the partial negative regions. But if you notice, there is a plane of symmetry this time right down the middle, and those two dipoles then cancel with each other. If they're pointing opposite directions, they cancel. So I'm really glad I reviewed this because our answers were wildly different on the poll. And the correct answer there was only CO2. Okay, so if you have questions on that, please hang around after. We can review some of that some more, but please revisit polar bonds and molecules because that's going to be on the exam for sure. All right, now to chapter 5. We're going to look at common types of chemical reactions. So these are going to be 3 new ways to classify chemical reactions. So don't forget the previous 5. We're going to look at 3 more ways today. Okay, so the first way, I'm just going to jump right in. These are known as precipitation reactions. Okay, so you guys are familiar with what a precipitate is, right? We looked at this on the wet lab that you guys came in to do. And this occurs when you have water-soluble reactants, okay, things that, what does water-soluble mean? It means you have a chemical, a compound that is dissolved in water, okay? That's what water-soluble means, dissolved in water. And they react to form one or more, you can get more than one even, insoluble products. So you have these dissolved soluble reactants, and they're going to react together and they're going to form things that are no longer able to stay dissolved. And when that happens, we use the phrase, we say it falls out of solution, okay? And it appears, and that's what a precipitate does. The insoluble product is the precipitate. So here's an example. You see this reaction over here, this really bright yellow compound. This is lead iodide, okay? This is PbI2, lead 2 iodide. And if we look, that's shown right here in this reaction. So this started out with a solution. Remember these phrases or these abbreviations we said that show up after a compound, telling you the physical state. AQ stands for aqueous, and aqueous is something that is dissolved in a solvent, in a liquid. So we have lead nitrate, okay, lead 2 nitrate. And we have potassium iodide as well. Okay, these are both aqueous. These are both compounds that are dissolved in their separate beakers. And then when you mix them, when they react, so that's when you see one is being poured into the other. So they're going to react when they're mixed. You're going to form potassium nitrate, which is aqueous, still dissolved in the solution. But the lead iodine is no longer aqueous. It becomes a solid. And that solid, that parentheses S indicates to you that's your precipitate. So here, indicating the physical state of the matter is crucial. That's going to be a key indicator to you that you have a precipitation reaction. Now, you won't always, like on that worksheet I showed you for bonus points, you may notice that the physical states are not indicated there. So how are you going to tell if something's a precipitation reaction on that worksheet, for example? Well, we have a list of things called solubility rules. And we're going to look at what compounds tend to be soluble and what compounds tend not to be soluble in water. And you're going to have this chart available. You don't have to memorize everything on it, but you need to know how to look at it and read it. So this is an example of a precipitation reaction. And usually if the signs are there and you see that one thing is soluble, or sorry, a solid, not soluble, then that's a precipitation reaction. And then also, if you had to classify this reaction, how would you classify it from the ways we learned Friday? So besides it being a precipitation reaction, is this a combination, decomposition, single, double displacement, or combustion reaction? What would you guys say? Kylie says double displacement. Anybody agree or disagree? Okay, Gabby, I would love to look at your homework question after lecture's over. Stick around, we'll look at it, okay? So this would be, I agree with Kylie, a double displacement reaction. You have, as your reactants, look at these, we have two ionic compounds. Okay, here's your cation. I'm gonna box in the cation in blue. Here's your cations, and then your anions are the ones in red, okay? So when you have two ionic compounds, that is double displacement, okay? The only way they can react is rearranging your cations and anions. All right, so here's the list of solubility rules, what I mentioned earlier. And what it shows you are that compounds will be soluble if they contain anything under this column. They will be soluble, okay? They will dissolve, they will be, in other words, aqueous, okay? So, for example, if a compound contains ammonium in it, if ammonium is the cation, that compound is soluble. No exceptions. It's always going to dissolve. It's always going to be aqueous. All right, same for lithium, sodium, potassium. What do you know about these? These are all main group 1 elements, alkali metals, okay? Nitrate, if this is an anion. So these top 4 are your cations. These are cations. The rest of these down here are anions. So if something has nitrate as the anion, it's always going to be soluble. No exceptions, okay? It will dissolve. If it doesn't matter what the cation is. If nitrate's the anion, it's going to be dissolved in solution. Perchlorate, that's a weird one. We haven't talked about that much. Acetate. There's different ways to write acetate. I want to point this out, by the way, because on your lab, you saw it written CH3COO minus. Here you see it written CH3CO2. Sometimes you also see it written C2H3O2. Okay, this is all acetate. I'm sorry, there's so many different ways to write it, but there's 2 carbons, 3 hydrogens, 2 oxygens. So don't be thrown off by the way it's written. Acetate compounds, these are always soluble, will always dissolve, they're always aqueous. Now, the way this gets complicated is down here with some exceptions, okay? These compounds, your halogens, by the way, except for fluorine, so just chlorine, bromine, and iodine. If these anions are in a compound, that compound is always going to be soluble and aqueous unless it's bound with these 3 particular cations, okay? Silver 1, mercury 1, well, it's a Hg2 plus 2, and then lead 2, okay? So in other words, for example, if you have well, I'll need to write the cation first. If you have AgCl, that compound will not be soluble because there, silver is the cation, okay? If you have Hg2Cl2, that compound will not be soluble. It will be solid, okay? It will not dissolve. So same thing if we had lead chloride, and you can apply that to bromine and iodine as well, okay? Sulfate compounds are soluble. They will dissolve. They will be aqueous unless it is combined with any one of these 3 cations. Okay, I know this definitely complicates things, but this is why you're going to have this chart available to you to just directly read off it. So that means barium sulfate is going to be a solid. Mercury 2 sulfate will be a solid. Same thing with lead sulfate, okay? So these will form solids, these will form precipitates. So you need to probably be able to recognize some of these. All right, so that's it for solubility rules. So let's have a poll question now. Based on our solubility rules, based on what we just talked about, which of these following compounds are soluble in water? I have a poll question. I'm going to launch it. Okay, so these are lettered off A, B, C, D, E. So that's how I want you to treat the poll question. A corresponds to cadmium carbonate. C, D, CO3. B is the lead sulfate. Okay, so which one? Check all that apply. I think you should be able to check multiple. Can you select multiple answers? Okay, so anything that is soluble, click on that one. All right, I'll give it just a few. Well, we're only halfway there. If you don't have access to the slides, you're going to need to be able to look at the solubility chart. But I don't want to scroll up because I need people to be able to see the answers. All right, we're going to go over these. So if you're totally lost on this, we're about to go over the answers in a minute. All right, 15 more seconds. And that should have been enough time. All right, I'm going to go ahead and shut it down. So get your answers in if you've not. All right, share results. So ignore the fact that one of them is in red. The 2 most commonly picked answers were the last 2. Okay, so sodium sulfide and ammonium phosphate. So let's look at these. A, CdCO3. So let's go see. All right, is cadmium, which is Cd, is that on our solubility chart, and is carbonate? And if you look through every cation and every anion, neither one of those are on there. Okay, so what that means is this is going to form a solid. This is not going to be soluble. It will not be aqueous. Okay, it's not aqueous. So it will not be soluble in water. It will form a solid. Okay, so you should not have selected A. All right, lead sulfate. Okay, so sulfate's down here, and sulfate is generally soluble if it's present in a compound unless it is combined with lead. Okay, so lead sulfate will also form a precipitate. Okay, when lead is the cation, it makes that compound insoluble, so it will also not be aqueous. All right, what about mercury 2 chloride? We actually wrote that one here as an example, right? So anytime chloride is present in a compound, it's usually soluble unless here mercury is the exception. So that one is also going to be a precipitate. Okay, what about sodium sulfide? D, well, anytime sodium is the cation in the compound, it is always soluble. Guess what? No exceptions. Okay, so that one will be I don't know what happened. That one will be aqueous. Okay, so you should have selected D. It will be soluble in water. And then ammonium phosphate, if you go back up as well, ammonium is the very first one. Anytime ammonium is present in a compound, that compound will be aqueous, no exceptions. So questions on how to use the chart. So you should have selected this as well. This one will be soluble. Whoops. Any questions on that? So if you can identify one of your products, not a reactant, but a product as a precipitate, that is a precipitation reaction, okay? And another key is it's usually a double displacement reaction. Usually, I'm not gonna say always. All right, let's do one more. What products will be formed? You have two ionic compounds here, so this is definitely double displacement. So what products will be formed, and will they be soluble or insoluble? So try to write out your products based on how you know double displacement works. Remember, the cation switch and bind with the opposite anions. And what's majorly important is that you write the correct chemical formula, a compound that is charge neutral. So I'm going to highlight in blue my cations and in red my anions, okay? So in each compound in your product, you need to have a red and a blue. You cannot put two blues together and you cannot put two reds together. So I'm going to take the blue cation from the first compound and put it with the red anion from the second compound. So that is going to be, I went too far. That's going to be these two right here, silver carbonate, okay? So here, what is the charge on silver? Can anybody help me out with the charge on silver? Oh, I need to stop sharing the poll, sorry. What's our charge on silver? Brooklyn says a +1, and she's correct, okay? That is a +1. Silver is one of your transition metals that always is a +1, no matter what. It never varies, okay? You could also have figured that out if you're looking at your anion, and you know nitrate's a polyatomic, and it carries a -1 charge overall. And you only have one silver here, so that one silver cation has to be +1. So if we're going to combine silver with carbonate, we know carbonate is a -2. It's just a polyatomic, and we know that from looking at a polyatomic chart. We need two of these. So it's got to be Ag2CO3. And is that going to be aqueous, or is that going to form a precipitate? What do y'all think? Kylie says aqueous. Any other thoughts? Let's look at the solubility chart. Is silver or is carbonate, CO3, on your solubility chart? I'm gonna erase all my scribbling because it makes it hard for me to read.
Silver is on there.
Do what?
As an exception. Yeah, silver is on there as an exception.
When silver is on there as an exception, when it is combined with chlorine, bromine, or iodine. Okay, when that's
right.
Here, chlorine, bromine, or iodine is not your anion. Carbonate is. Okay, so it's only when silver is combined with one of these three anions. I know that's complicated. I know that's nuanced, but that's how it is. Okay, it should be solid. So we're going to put an S there for solid. Yes, silver's on there, but only when silver is combined with chlorine, bromine, or iodine, it does it form, form a solid with those, anions. And here, carbonate is your anion, so carbonate this is definitely a solid. Okay. How do you know it is a solid? Okay, let's go back to the solubility chart. So we have this compound, Ag2CO3. What's listed on this chart tells you if it is soluble, if it is going to be aqueous, right? And that's what we're trying to decide. Is it going to be aqueous or is it going to be solid? If it's present in this list, it'll be aqueous unless it falls into the exception category, and then we said it's going to be a solid. So for the example we gave, silver chloride or mercury chloride, these forms precipitates. These are solids, okay? So silver and carbonate, neither one are on this list. So it's definitely going to be a solid. Anything that's not on this list is going to be a solid. It will not dissolve. Okay. It's aqueous if it's on this list. And if it's not, unless it's an exception, then it forms a precipitate. And if it's not on the list, it forms a precipitate. Does that help, Gabby? I don't see silver and I don't see, I mean, I do see silver down here, but again, this time it's only pertaining to these 3 anions. Gabby, what do you mean? What about liquids? Help me understand your question a little bit.
Like, how do you know that it's like not like how do you know that it's going to be a solid and not like 2 liquids? You know what I'm saying? Like, how do you know if it's not on this list, it's a solid?
I mean, this is done. This list has been done through experiments. They've done experiments to tell.
So like, there's no like it's always going to be a solid if it's not on it. It's like all is like the question.
Yes, if it's not on it. So for example, silver carbonate's not on the list. Does that make sense? We don't have silver as one of our cations that is soluble, and we don't have carbonate on the list. So neither one, the cation nor the anion, are on the list.
Okay, sorry, go ahead.
Because it's not on the list, that's how we know it's going to be a precipitate. I feel like there's still questions on this.
Yeah, my thing is about liquids and stuff. So later in the chapter, it says something about liquids, like maybe like redox or like acid-base reaction. That's what I was meaning.
Okay, so when we get to acid-base and redox, we'll talk more about that. But just for the sake of precipitation reactions, if you're looking at this list trying to decide, like we are in this question, is it going to be a solid or not? We're just assessing. We're not really assessing is it a liquid or not. We're assessing does it dissolve or does it not dissolve. Does that help? Kind of. Okay. Okay. If you still have questions, then please hang out around after lecture. I feel like there might still be questions and people are just afraid to ask maybe. If there is, please hang around. I'm happy to dig through this further. But if people feel okay with it, I'm going to assess the other product here. The other product that we're going to form, I'm going to do this in green, will be this cation with this anion. Okay. So sodium nitrate. So let's write that out. Sodium is a +1, it's main group 1, and nitrate's a -1, it's a polyatomic. So it's just NaNO3. And this one is for sure going to be soluble. How do we know that? Look, sodium is on the list and nitrates are on the list. And anytime those are present in your compound, always soluble, always aqueous, no exceptions. Are reactions that trade hydrogen atoms generally acid-base? Yeah, you guys are ready to jump into the next thing. Y'all are like, quit talking about precipitation reactions. I want to talk about, yes, that is a good question, Nadia. And I'm actually going to get to that on the next slide. Okay, so that one's aqueous. So there you go. That's how you work this problem. Definitely be able to work something like this for the exam. Okay. Have I talked about precipitation reactions long enough? All right. 2, acid-base reactions. So going to Nadia's question, are reactions that trade hydrogen atoms generally acid-base? Absolutely. That is yes. The answer to that is yes. Acid-base reactions, this is the second major type of classification. These commonly occur between an acid, okay, and we're going to abbreviate the acid as HA. This is an important thing to know, HA. Because acids, A stands for acid, by the way. It's the anion portion of the compound. So you can think of it as anion, you can think of it as acid. This H plus right here, this is a hydrogen ion. This is what acids do. They donate or they give away hydrogen ions. We're going to hit this really in depth in chapter 10, but for now, just know that this is the abbreviation we use for acids. So it occurs between an acid and a metal hydroxide. Okay, and we're going to abbreviate this MOH. Okay, we know hydroxide is OH minus. That's a polyatomic. So M here stands for metal. It could be any metal. Let's list some examples. It could be lithium hydroxide. You could have sodium hydroxide. You could have barium hydroxide. That would be OH2. You could have calcium hydroxide. That would be OH2. All these are really strong bases. These are just examples. All of these first elements right here, these are all metals. Okay, so the M stands for metal. All right, now I'm going to tell you this is a very narrow definition of an acid-base reaction. Okay, there are many, many other kinds of bases. We're just looking at one narrow example here, and then I'm going to really expand this when we get to chapter 10. Okay, but for now, this is good enough. So and by the way, it yields water and a salt. Okay, two very harmless compounds. Okay, we know acids and bases can be very corrosive, very toxic in some regards, and it makes two very neutral things. How nice. So here's our acid. All right, how did I know that? Because of the abbreviation HA. And here is our base. The metal hydroxide is the base. All right. The acid is going to give away an H plus. So it's going to break apart because it's aqueous. It's going to break apart into two things, right? H plus and A minus. And that's why we're calling A minus the anion part here of the acid. Right? So the base is going to also break apart. It's aqueous. And this is what they do. They dissolve. You're going to have the metal cation and the hydroxide anion. And then things are going to rearrange just like a double displacement reaction, right? So your H plus and your OH minus, these are going to come together. What does that make? Water, H2O. And then what's left, your anion part of the acid is going to combine. It's going to be attracted to the metal because there's opposite charges here, positive and a negative. We know metals always form cations that are positively charged. And these things are going to form the salt, okay? And that's what is abbreviated here, Ma. Ma is just the salt. You got a cation and an anion, okay? All right, so what we just talked through is written in sentence form down here. The H plus, the hydrogen ion from the acid combines with the hydroxide anion from the base to give neutral water. We just walked through that. And then the anion from the acid, okay, that was the A minus part that I circled in red, combines with the metal cation from the base, and that's going to give you the salt. So I want you to look at, based on what we just did and how we see things rearranged, just like a double displacement reaction, look at this reaction down here. We have acetic acid. This is acetate, okay? You should recognize that polyatomic ion. And when you put a hydrogen on it, it becomes an acid. It's acetic acid. This is the acid in vinegar, by the way, if anybody's ever used vinegar. So it kind of smells. You can imagine what acetic acid smells like. And then we got sodium hydroxide. This is a really strong base. Okay, so this is your acid, and this is your base. All right, now I know the hydrogen is listed at the end, and you're like, well, I thought the hydrogen was listed first. And yes, you're right. Here, the hydrogen is listed at the end. And it doesn't matter. Don't let that throw you off. It's still the acid, okay? So what products are we going to get? How are these things going to break apart and rearrange? Well, one product you should always know right off the bat is going to be what? What's our first product?
H2O.
Water. Yep. That's a liquid. What's our other product here? The salt. Can anybody tell me what the name of it is? Surely someone can. I'm going to hold out. No one can tell me what the other product is going to be. I don't believe it. Thank you, Bradley. Sodium acetate. Okay, Na, and then CH3COO. Or if you wrote it C2H3O2, that's fine as well. Remember, there's like so many different ways to write acetate. And this is aqueous, because remember, anything with sodium is always soluble. Okay, questions on acid-base reactions. The key indicator here is that water is a product. Okay. All right, one more practice problem, and then we've got to move on to redox reactions. Write and balance the equation for the following acid-base neutralization reaction. So sometimes we just call them acid-base reactions, but the full term is acid-base neutralization. Why is it called neutralization? Well, water is a neutral compound, okay? Neutral, pH 7. I know we haven't talked about the pH scale yet, but they form things that are neutral in pH. So that's why we say acid-base neutralization. So, all right, we got cesium hydroxide and hydrogen sulfate react to yield what? So here you actually have to write out the formulas for your reactants. You're welcome. I know you love me. Write out the formula for your reactants. Cesium, you're going to need a periodic table. Cesium hydroxide, I'll give you a little help if you don't have one. This is CS. And cesium is main group what? Anybody know what main group cesium is part of? Main group 1. So guess what? As a cation, it'll be CS plus 1. And then hydroxide we know is OH minus. So how do you form a compound from these? You get a plus 1 and a minus 1. So anybody want to tell me what you wrote out for your 2 reactants? Okay, so we got CS. Sorry, somebody was talking. But Tia wrote it in the chat. CSOH is the first one. Who was going to tell me one?
The other one would be hydrogen sulfate.
Yes, but what is the formula for that? Gabby says HSO4. What do y'all think? Diatomic? Tia said H2SO4. So remember, sulfate is SO4 with a -2 charge. Hydrogen is main group 1. So how many hydrogens and how many sulfates do you need? Yeah, we don't write it H2 in here because it's a diatomic, even though it is a diatomic. Remember, diatomics are just for when you're writing the element by itself. Like if I'm just writing hydrogen by itself, then I'm going to write H2. But here, hydrogen's in a compound. The only reason we're writing H2 is because we need 2 cations to balance the anion. Okay, so that should be your 2 reactants. Okay, then what's going to happen? We know how acid-base reacts. They're going to form water is going to be 1. We're forming water because we are taking the anion from the first one and the cation from the second one. HOH, H2O. Okay, and then the other compound that we're going to get, I'll do these in green, should be cesium with sulfate. Okay, so we're going to get plus CS. And how many cesiums will we need? Yeah, we're going to need 2. 2 of those, SO4. Whoops, there it is. Okay, and this should be AQ, soluble. Not a solid, it should be soluble. Remember, S only stands for solid, so don't think that S stands for soluble, although that would make sense, right? AQ stands for soluble. All right, questions on acid-base reactions? I have no idea how this is sinking in with everybody. That's honestly one of the hardest parts of online for me. I cannot gauge you guys at all from Zoom, hardly. I can only see like 10 faces at a time. Good, can y'all give me a thumbs up or a thumbs down at all? I'm looking. Okay, I like the emojis, thank you. We should do this more. So as well. Okay, if you feel a little shaky, that's fine. Anybody have another emoji that you want to give? Okay, I'm seeing some thumbs up. I'm not seeing any thumbs downs. Anybody just like not getting it at all? Okay. Well, we're gonna keep moving and then we'll do some review as well. I want to talk about the last classification, which is redox reactions. So I actually want to do a little intro on this because redox reactions are really powerful and we depend on them every day. Okay, so I have a lot of pictures here, and my question is right here. What do all these things have in common? So what pictures? Anybody can tell me what's in the pictures? Can you name one of the things? What do y'all see?
There's a cochlear implant on the right.
Yes. Okay. So Gabby said here, that's the cochlear implant, Gabby. So this is not just a hearing aid, it is a cochlear implant. I don't know if I spelled that right. I don't think I did. It just might be LAR. Cochlear implant. It does help people who have trouble with auditory signals. It helps them take what auditory signals they do hear and transmit it so that they can, there's a transmitter on it and a speech processor, so it helps them actually be able to hear verbally, speech. Okay, somebody said a pacemaker. This one over here is a pacemaker. Okay, my grandfather was in the hospital a couple of years ago with congestive heart failure. And they wanted to put a pacemaker in him, but he was kind of a high risk. He's in his 80s. So at that point, it's really, they just give you medication when you're that old. So, but pacemakers help keep your heart in rhythm, right? And then down here, anybody have somebody in the military or somebody that has dealt with PTSD before, you can get brain implants for that. And that's kind of a big decision because those obviously can alter your life in a lot of ways. But they can help balance out your nerve impulses and your emotions and things like that. So all of these things, what do they have in common? That's the question. Any thoughts? An electrical charge, Chelsea said. You're getting at the right idea. They all items that can help change someone's life. Yes, they're all impactful in big ways. Implants in your body. Stability, these are all great, all transmit something. Yes, they all, I like kind of what Chelsea said at the first, electrical charge, they all have small batteries, okay? They all run off of small batteries, really, really small batteries. And think about how much our lives depend on batteries. Anybody, your cell phone loses its charge at like 10 in the morning? Anybody at that point yet? Okay, we depend on them, right? So we're always charging things, charging our computers, we depend on batteries. And that is how redox reactions run. Redox reactions run batteries, essentially. So if we didn't have redox reactions, we would have no batteries. Life as we know it would not exist. So what is a redox reaction? Well, it stands for oxidation, reduction, reaction. And we abbreviate them redox. Okay, the most blanket statement I can give you for what a redox reaction is, it is one in which electrons, you thought you would never hear that word again, electrons are transferred from one atom to another. So you are very, very used to this idea of electrons being transferred. Okay, so this should not scare you. This should not feel new. You are very familiar with an electron going from one atom to another. That's how we formed ions. We know how to count valence electrons. We've done this for a long time now. So we're going to dig into this a little bit and we're going to look at it within the scope of a whole reaction. So that's going to feel more complicated than normal, but please remember that you're very familiar with the transfer of electrons. Okay, so I'm going to define the two terms. Oxidation, this is when something loses electrons. Okay, oxidation is the loss of electrons. So if something is becoming a cation, it was oxidized. Okay, if something is increasing in charge because it's giving away negative electrons, it's being oxidized. So if you're looking at this chart over here, anything that you read from left to right is a process of oxidation. Something does not have to just become positively charged. We could have something that's going from a -2 to a -1 charge. You see that? That is oxidation. Why? Because it's giving away an electron. It's increasing in charge. Even though it's still negative, it increased by 1, right? -2 to -1 is an increase of 1. Okay, so that's oxidation as well. So don't just get it in your head that it goes from 0 to +2. or 0 to +1. It can, and that is oxidation, but it can also go from -1 to 0. Okay, that's oxidation as well. So anytime something is losing electrons, the charge will increase by 1 or 2 or 3. That is oxidation. Reduction, this is the gain of 1 or more electrons. Okay, so if you read the figure in reverse from right to left, you see that we are taking an electron. I'm going to just read the bottom one here. Taking an electron, we're adding it to the element. Okay, any sort of atom here. Here, if it has a +2 charge and it gains an electron, it's going to end up as a +1 charge. If you have a +1 charge and you add an electron to that, you're going to be neutral again. You see how we're decreasing in charge as we go? That's because you're adding an electron to something. Now, people get all kinds of confused because when you say something gained an electron, you want to think, oh, that was oxidized. It gained something. No, remember, electrons carry negative charge. So if you gain an electron, you decrease in charge. You're looking at the charge here, the change in charge. Okay, and that does happen through electrons being transferred, given or received. But keep in mind that it's the charge that you want to track. Okay. So anybody heard the phrase oil rig before as an acronym for how to remember this? So oxidation is the loss of electrons, OIL, that's the oil part. Rig stands for the reduction, is the gain of electrons. Reduction is the gain of electrons. That's the rig part. So if you get confused on, oh crap, which way does it go again? Oxidation, reduction. Remember oil rig. Oxidation is the loss of electrons, and you're increasing in charge when that happens. Reduction is the gain of electrons, and it is the charge that is reduced. And the charge over here is increased. All right. Okay, so now let's look at this in the context of a chemical reaction. And we're going to track which element is oxidized and which element is reduced. Which one gave away electrons, which one received electrons. All right, so we have copper, just solid metal copper, elemental copper. And then we have silver nitrate. All right, and it's aqueous, it's soluble. These things are going to react, and you're going to form silver metal, okay, and copper nitrate. So it's kind of like the copper and the nitrate, or sorry, the copper and the silver just switch places. You see that? So first off, is this a combination, decomposition, single displacement, double displacement? What kind of reaction is this? Anybody recognize? Chelsea, Ashton, Kylie all say single displacement. Rachel says single displacement. That's correct. Okay, you have one ionic compound. And then you have one element. Okay, and it's just it's a metal. And we said metal displaced cations, right? And that's what happens in this case. The silver is displaced, and then you have copper nitrate. So here's what I'm going to ask you. What things are changing charges? What happens to the copper and what happens to the silver when it comes to their charges? On the reactant side, does copper have any kind of charge starting out? Does it have any kind of, if you had to assign a number to it that represented its charge, what number would you assign it? As an element, it's not an ion, so it should have what number assigned to it? Thank you, Nadia. It should have a 0, okay? And that's what you see down here, 0 charge starting out, okay? Now, over here though, when it's copper nitrate, now what number would you give it if you had to assign a charge to it? When it's in a compound, you've already figured out how to write ionic compounds. You already know the rules for how to do this. Chelsea says 2. Anybody agree or disagree? Should we give it a positive 2? Well, we know nitrate is a -1, and we've got 2 of them. So times 2, we've got -2 total, and we know it has to be balanced to 0, right? So the cation here has to be a +2. So here, if we had to assign a number to copper, it would be a +2. Okay, so what happened to copper? Let's answer our question. What happens to copper? Charge-wise, it goes from 0 to +2. Okay, you guys see that? When it's by itself, it's a 0. When it's in a compound, now it's a cation. So would you say it's oxidized or reduced? Did it gain or lose electrons based on what we just talked about and the definitions? Chelsea says, Bailey says, oxidized. That is correct. Okay, now the second question is what happens to silver? Okay, yes, so copper is oxidized here. Well, silver starts out in the compound. So if we had to assign a number to silver to give it any kind of indication of what kind of charge it carries, what number would you give it? Kristen says a 1. We got to vote for +1. That is correct because we just have 1 silver and 1 nitrate. And again, we wrote over here, we know nitrate carries a -1 and it does so. It's just, that's what it carries. It's a polyatomic. All right, so silver starts out as a +1 and over here it's by itself. So what charge would you give something when it's by itself as an element? Yeah, you would give it a 0. So what happens to silver? Well, silver starts out as a +1. And on the product side, it becomes a 0. So was it oxidized or reduced? Did it gain or lose electrons? You only change charge if Kristen says reduced, and she's correct. And Brooklyn said that as well. Okay, that's what this whole figure down here is representing. Okay, it's telling you it starts out copper as a 0 charge, and over here it's a +2 charge. Okay, silver starts out as a +1 charge, and it becomes a 0 charge. Okay, so what you're noticing is when elements are by themselves, they have no charge because they're by themselves. That's how they exist in a natural state. They have not given or received any electrons. They have the same number of electrons as they do protons when you have elements by themselves. Does that make sense, Gabby? Yeah. So they're neutral charge when they're by themselves. Same number as electrons as protons, neutral atoms. All right. So copper. Copper lost 2 electrons, right? That's what happened to copper. Silver found those 2 electrons, okay? Silver gained. I'll write it in blue. Now, you have 2 silver atoms, okay? So each one gains 1 electron. The charge only changes by 1, so each silver atom picks up 1 electron, all right? So here's a picture of that, by the way. You have a copper wire in a solution. This was the silver nitrate. It's a NO3. That's the solution, and then you have the copper wire. And look what happens to the copper wire. It looks all furry and fuzzy. That's silver forming on the copper wire as it reacts. And then the solution turns kind of a greenish blue color. Anybody seen copper turn kind of a greenish blue color when it's left out in the weather? My husband thought it'd be a really good idea for his first wedding band to be copper. And his finger literally was like green all the time because he'd wash his hands. So don't ever do that. Don't ever pick a copper ring. Okay. All right. Redox reactions, just a summary here. They involving ionic compounds are usually straightforward. And you're like, yeah, right. They don't feel straightforward. Okay. But if you can track the change in charge, you're looking at the change in charge to determine which compound is reduced and which is oxidized. Okay. There's another example here. So I would love for you guys to look at this. You have potassium iodine and you have bromine, and you even have some extra information beneath. I want you to fill in iodine ion. Is it oxidized or reduced? Look at it based on what we just talked about with oxidation reduction. Is the iodine, is it oxidized or reduced as it charge increases from -1 to 0? So iodine starts out in the compound over here with potassium. It's an anion starting out. So starting out, iodine has this charge assigned to it, -1. That's the number we would give it to represent what kind of charge it would have. But on the product side, we see that we form iodine as a solid, and it's just elemental iodine by itself, a neutral element. So it has 0 charge. So if you go from -1 to 0, iodine ion is, would you guys say oxidized or reduced? Chelsea says oxidized. Ashton says oxidized. Remember, oxidation is the loss of electrons. When that happens, your charge increases. So it's oxidized. All right. Bromine, over here on the reactant side, bromine, we're talking about bromine now, just elemental bromine. So it has no charge, even number of protons and electrons. But on the product side, it's involved in a compound, KBr. And there it becomes an anion with a -1 charge. And that's what you see here. Bromine starts out with no charge, but on the product side, it does have a -1. So bromine is, what would you guys say? From 0 to -1, is it oxidized or reduced?
Reduced.
That's correct. As its charge decreases from 0 to 1. Okay, so I have no idea how you guys are feeling about this. Thumbs up or thumbs down? I'm gonna click through my screens. Give me a thumbs up or a thumbs down, or whatever emoji you wanna give to represent yourself. Okay, I'm seeing a few different ones. Seeing some no responses. Okay, well, mostly I see, okay, Molly said, what would K be? So here, Molly, I'm glad you actually asked that. Let's look at potassium for a second. Potassium on the reactant side, you're right, we did not address potassium. The reason we don't address potassium here is because it actually doesn't change. What charge would you give potassium on the reactant side here? It's the cation. We know potassium is main group 1, so yes, Molly, it would be a +1. It's a +1 on this side, and over here, it's still in a compound, it just has a different anion. So what charge would you give it as well on the product side? Still +1, that's correct. So potassium is a +1 on both sides, so it doesn't change. So if something is not changing charge, then it's neither oxidized nor is it reduced. Okay. All right, what we've been doing without me even telling you is we've been assigning oxidation numbers, and these feel very much like charges, okay? So if you want to think of them as charges for now to help you, that's okay. I just want to point out the fact that oxidation numbers are different from charges. I'm about to sneeze, maybe not. This is on page 151, 152 of your textbook, and if I can implore you to do anything, please just, it's 2 pages. Please just go read it, okay? I'm gonna walk you through it here, but I think you'll get a really good firm understanding if you'll just go read these. I've never begged you so much in my life to read 2 pages of your textbook, okay? Please just go read these 2 pages, and I think it gives lots of great examples. I'm gonna hit it here, but I think that'll help you if you'll go read that. What are oxidation numbers? They are numbers assigned to atoms to indicate if they are electron rich, electron poor, or neutral. All right. So that's what we've been doing. We've actually been assigning oxidation numbers. And sometimes you will find the more you get into redox reactions that oxidation numbers are different from charges. Okay. Sometimes elements can carry oxidation numbers and they can be electron or rich or poor in a way that's different from a charge they would typically carry as we know them as ions. Okay. We know ions, we can predict ionic charges. Oxidation numbers can sometimes be different. So you can tend to think of them usually as charges, but sometimes things are different. So they do not necessarily imply charges. A few rules for when you're assigning charges or oxidation numbers, sorry. In its elemental state. So anything by itself, that's what we saw with copper. We said solid all copper by itself in its elemental state, or iodine, when it's by itself, we know it's a diatomic, okay? Anything that's by itself in elemental state, oxidation number of 0. It's neutral, okay? A monatomic ion. Okay, here, monatomic, standing for a single ion. That's going to have an oxidation number equal to its ionic charge, okay? And that's what we typically saw. Usually we assigned a number that was just equal to the charge it would have if it was an ion, okay? And these will never vary for certain elements, like chlorine. Chlorine's always going to be a -1, and the oxidation number you'd always give chlorine is a -1. Sodium. Sodium's a main group 1. Any main group 1 element, its oxidation number will always be equal to its charge as an ion, okay? So that's what rule two is getting at. In a compound, an atom usually has the same oxidation number it would have if it were a monatomic. This feels very repetitive, okay? And that's why I say there's a lot of overlap between charges and oxidation numbers. In a compound, you're going to ask yourself, okay, and that's what we did up here. I'm going to scroll up for a second. That's what we did up here. We said, oh, iodine right here. If we had to give it a charge to represent if we had to give it an oxidation number to represent its charge, what would you give it? A lot of people said -1, okay? Or you thought -1. And that's what we said over here. It's a -1. And it's in a compound, but we're giving it an oxidation number equal to its charge as an ion. Okay, that's what rule 3 is saying. And then the sum of oxidation numbers in a neutral compound is 0. This example is walked through in your book very, very nicely, okay? Because again, sometimes you're going to see the oxidation numbers do not follow charges. If we were to look at this, okay, you have a nitrogen, and I'm not going to draw all the bonds exactly correctly, but this is how the compound looks. There's some double bonds in there, but just ignore those for now. If we had to assign oxidation numbers to every atom in nitric acid, how would we do this? Okay, I'm going to show you what it is right now, and then we'll walk through it briefly. All the oxygens are going to be -2, okay? We know that's what oxygen typically does anyways as an ion, usually -2. Oxygen is pretty predictable, okay? Hydrogen, we know, usually carries what kind of a charge? It's main group 1, so that should have a +1. So if all these have to add up to 0, what does nitrogen have to be? If all of our numbers here have to add up to 0, the sum of everything, Maria says nitrogen has to be a +5. And I agree with you. We've got -6 and we had a +1, so nitrogen has to be a +5. So that's bizarre, right? We usually don't see nitrogen forming a +5 oxidation number, but here its oxidation number is a +5, all right? And the way you figure that out is you put the oxidation numbers on the elements you do know. Things like main group 6, main group 7, main group 1 and 2. Those are going to be predictable, not vary. But the sum of all oxidation numbers in a neutral compound are 0. And that's why nitrogen had to be a +5 here. Okay. All right. We are getting close on time. And I want to look at this last example of a redox reaction. And that's all we have time for today. So last one, and then there were several other, I had a poll question I was going to ask on one of these, but there's a few things we're just not getting to here. Okay, so let's look at one more example, and then I'll just field questions. And if we need to cover anything Thursday, we will. We'll see. I have 2 of the same slides here. Sorry. Let's just go with this one right up here. It says, which element is oxidized and which is reduced in the following reaction? Tip, always go through and assign your oxidation numbers. So if you're given a reaction and I'm asking you, is this precipitation? Is it acid base? Is it redox? One helpful tip is that if you have a single displacement, sometimes you can identify that as a redox reaction. Here, what kind of reaction do we have? We have Si, silicon, and chlorine coming together to form silicon tetrachloride. That's right, it's a combination reaction, okay? So if we were to assign oxidation numbers here, how would we do that? An element, we have 2 elements by themselves on the reactant side. Silicon by itself, chlorine by itself. So what kind of oxidation numbers do you want to give those things? Kristen says 0. Brooklyn said both. That's right. So we're going to give 0 and 0. Remember, anything about it's rule number 1. But on the product side, we've got to give oxidation numbers, and the sum of those have to be 0. So how do we want to assign oxidation numbers here? You need to give the positive oxidation number first and the negative oxidation number second, just like you would in an ionic compound. The cation first, the anion second. Here, the positive oxidation number first, and negative oxidation number second. So what do you guys want to do? What oxidation numbers y'all think we should give?
+4 and then -1 to chlorine.
-1. So with that added to 0, I see we got 4 chlorines. So we actually have 4 times -1 if that's the case, because we got 4 of those chlorine atoms. So that would multiply out to -4. And I agree that a +4 and a -4, because we only have 1 silicon. Okay, we don't have to multiply it by anything. You can multiply it by 1 if you want. That adds up to 0. Okay, so I like that. +4 and -1. So now if we're trying to say what was oxidized and what was reduced, the way I like to write it out is I say, okay, I got silicon is changing and I got chlorine is changing. Starting out, both of these things were 0. And on the product side, they're different. This one is a +4, this one is a -1. So now you can track exactly how the charges were changed. So silicon went from a 0 to a +4. So would you say it was oxidized or reduced? Remember, oil rig, oxidation is the loss of electrons and the charge is increasing. So this one is oxidized. And that means the next one, 0 to -1 for chlorine, the charge is reducing. It's going down. So this one is reduced. Okay, so that's kind of as far as we're going to get today. I'm going to launch that review that I've done. I just want to know, where are you guys? It's hard for me to tell. And I feel like what we talked about today is pretty layered and can be pretty complex. And you may feel good about it now. And then when the moment you try to go do it on your own, you may feel really confused. Okay. Attempt to do some practice problems on your own. Attempt to do this next one on your own if you can. All right, I'm going to end the poll because we're at time. And most people said 75% good, but if you are 50% or less, please reach out or stick around if you've got questions.